As a ship approaches port, her officers and crew must prepare for mooring. When berthed, the ship's mooring system must help ensure the ship's safety and enable cargo operations to proceed smoothly. The purpose of mooring is to ensure that the ship lies securely in the correct position at the berth, relative to the loading arms or cargo handling facilities, no matter how the wind, waves, or currents may affect her. In this video, we shall look at the various forces the mooring scheme must withstand, but mooring at buoys will not be considered. The forces that act on a ship's hull at a berth can be considered as having two components. Transverse forces, trying to move the ship away from or towards the berth, and longitudinal forces, trying to move the ship along the berth, forward or aft. These forces may be caused by wind or by the movement of water, such as underwater currents, wave motion and swell from passing ships. Wherever possible, berths are designed to minimize the transverse forces. In practice, however, changing wind, tide and sea conditions mean that such forces may present a load on the ship's hull from any direction, effectively reinforcing or counteracting each other. There are, of course, vertical forces acting, and we will deal with these later. Any mooring system employed must be designed to withstand most predictable changes in the forces acting on the ship. The most frequently used mooring scheme is made up of spring lines, fore and aft, to counteract the longitudinal forces acting on the ship, breast lines, fore and aft, to counteract the transverse forces acting on the ship, and head and stern lines, to counteract any forces which may cause the ship to yaw in the berth, due to the turning effect of the total force acting on the ship. Of all the forces acting on a ship's hull at a berth, the wind and current forces are the most severe. But to design a mooring system able to resist the most extreme conditions would be very complex and costly. Instead, the design criteria are based on the system being able to counter the longitudinal and transverse components of the forces associated with wind at 60 knots, or Beaufort force 11, plus a beam current of 0.75 knots, or wind of 60 knots, plus a current from a head or a stern of 3 knots. Remember that the wind and current forces are proportional to the square of their speed. So, the force of a 60-knot wind is 4 times that of a 30-knot wind. A 3-knot current would exert a force 9 times that of a 1-knot current. The ship's freeboard also influences both these effects. Wind speed increases with the height due to the reduction in surface friction. So the higher the freeboard, the greater the area of the ship that will be affected by faster winds, the higher the wind force assumed to be acting on the ship. In theory, a wind speed of 30 knots at 2 meters is likely to be 60 knots at a height of 10 meters and more than 75 knots at a height of 30 meters. When the ship is at rest, the vertical forces acting on it, dead weight downwards and buoyancy upwards, are in balance. During cargo operations, as the dead weight changes, so does the draft and the freeboard. This may have a significant impact on a mooring scheme. As we have seen, if the ship rises in the water, the wind force will increase. The current force, however, decreases due to a greater underkeel clearance. However, it is the change in wind force that is more critical for the mooring system, as this is much greater than the change in current force. For example, at force 11, the transverse wind forces may range from 100 tons to 370 tons or so, depending on the type and size of vessel. Longitudinally, these forces could range from 27 to 75 tons. Single lines would be unlikely to withstand the forces associated with very high winds. So, the basic pattern of spring lines, breast lines, head and stern lines are normally doubled up or even trebled to achieve the required mooring strength. It is inevitable that the lines employed at each position will be of different lengths and perhaps placed at different angles. However, different lengths of line will stretch by different amounts under load. The longer the line, the greater the stretch or elastic effect. This means that different length lines will take different proportions of the total load. The situation is even worse if you have to mix wire lines, high modulus synthetic ropes, and other types of rope. Wire lines and high modulus synthetic ropes have much less elasticity than nylon or polyester ropes. Wire and high modulus synthetic fibre ropes will stretch only by about 1.5% of their length, whereas the conventional synthetic ropes might stretch by 30%. So, the wire or high modulus line would take much greater proportion of the load if it was paired with a conventional fibre rope, possibly as much as 90%. Wherever possible, you should avoid mixing lines made of different materials. If this isn't possible, increase the flexibility of wire and high modulus lines by using synthetic rope tails. The ability of mooring lines to counteract the forces threatening to move the ship depends upon the angle between the direction of the forces and the mooring line itself. For maximum effectiveness, lines should not deviate from the horizontal. Unfortunately, this is seldom achieved. The effectiveness of a line is proportional to the cosine of the angle that it makes to the direction of the force it is resisting. For example, at 30 degrees, only about 87% of the load in the line will be resolved horizontally. At 45 degrees, the proportion reduces to 71%. When mooring lines change direction around rollers, fair leads, or Panama leads, there can be a further loss of effectiveness of up to 25%. This is because only a portion of the strands in the rope takes the load. The rest are compressed around the bend. The tighter the band, the greater the compressive force will be. To minimize this loss of effectiveness, you should select the routes for the line carefully to avoid severe changes of direction. How do we apply these theoretical rules in practice? Basically, the strength of any mooring scheme depends on the strength of each individual line. A weak line that parts could set up a sequential failure in the other moorings, as they would then be subject to additional loading. As a general principle, a good length of line should be employed to avoid the loss of effectiveness, which would arise, for example, in the case of a short and steep mooring line. Short lines have less capacity to stretch, and if short and long lines are combined, the shorter line will reach its maximum extension and part first under excess load. The breaking strengths of all the ropes and wires on board are known from the manufacturer's stated values. But through wear and tear, they will suffer an element of loss. To allow for this, a safety factor is introduced, and typically 55% of the maximum rated load is used to assess the available restraint. This factor also provides a margin to combat any additional dynamic loads which may occur. Whilst the breaking strength of an individual line is important, assessing the effectiveness of any mooring pattern depends more on the contribution that each line makes to the overall mooring arrangement. So, we can summarise the load factors affecting a mooring scheme as follows. 1. The effects of current and wind are considered as static loading. 2. These static loadings are calculated for maximum conditions of 60 knots wind, around force 11, and 0.75 knots transverse current, and 3 knots longitudinal current. 3. The ship's moorings are designed to withstand these loads. 4. The maximum rated load for a rope must be adjusted by a general safety factor and by factors relating to the orientation of the lines at any particular berth. On occasion, there are additional forces of a dynamic nature which can move the ship from her berth. These may come from waves, swell, or the interaction from passing ships. These can create powerful lateral and longitudinal forces. These dynamic loads could break the vessel out of her berth, unless restrained by a sufficient number of well-tended and tight mooring lines. So, all the lines must be correctly oriented and tensioned to prevent the ship from being able to range at her berth, causing damage both to the ship and the berth. To ensure this, the mooring lines must be frequently monitored. The winches, of course, are also a key element of the mooring system. The brakes are generally designed to hold a minimum load of around 60% of the braking load of the line, ensuring that the brake will render before a line parts. This value should be stenciled on each winch. To maintain the maximum holding power of a split drum winch brake, there should only be a single layer of wire or rope on the tensioning drum. This will provide the best use of the winch brake's holding power. A second layer would increase the radius at which the line would pull against the brake. The increased leverage could result in the brake being overcome. As an added bonus, the use of a tensioning drum avoids crushed layers of line on the storage drum. This is particularly important when using synthetic fibre ropes. All this theoretical knowledge has been applied to create a suitable mooring scheme for each port and each terminal round the globe. Most ships will have on board such books as the Guide to Port Entry 1995, which give all the basic information needed for mooring requirements for each participating port.
Yeah, we're looking for T's. Right. Not T's number 4, so that's the jetty here. Yeah. So let's see the mooring plan, what it says.
This information may also be available on CD. Updates can be obtained on the internet, which also provides the latest information for mooring. You may wish to watch this program again, and you should read the booklet that accompanies the video. For further information about mooring, you can consult the Code of Safe Working Practice for Merchant Seamen, issued by the Maritime and Coast Guard Agency, United Kingdom, and the oil company's International Marine Forum publications, Effective Mooring and Mooring Equipment Guidelines.